Ever pondered on the question, what makes the universe tick? It's a vast and intricate dance, choreographed by the laws of science. These laws, invisible yet omnipresent, guide everything from the spin of subatomic particles to the rotation of galaxies. Today, we'll lift the veil on 4 of these complex laws: quantum field theory, general relativity, the second law of thermodynamics, and Heisenberg's uncertainty principle. Quantum field theory offers us a framework for understanding the behavior of subatomic particles. General relativity, Einstein's masterpiece, redefines gravity as a curvature of space-time itself. The second law of thermodynamics predicts the direction and efficiency of energy transfers and transformations. And Heisenberg's uncertainty principle sets the boundaries for our knowledge of certain pairs of physical properties. Are you ready to dive into the fascinating world of scientific laws that govern our universe? Dive into the world of quantum field theory, the framework of constructing quantum mechanical models of subatomic particles. Imagine a universe of dancing entities, particles that twirl, spin, and leap in an intricate cosmic ballet. This is not a scene from a science fiction movie, but the very heart of our reality, the subatomic world governed by quantum field theory. This theory, quite fascinatingly, tells us that these particles are not just tiny dots whizzing around. Instead, they're more like ripples or vibrations in fields that permeate the entire universe. Just like waves on a pond, particles such as electrons and photons are excitations of these fields. Quantum field theory also presents a unique perspective on the nature of empty space. In this quantum realm, even a vacuum is teeming with activity. Fields are constantly fluctuating, giving rise to particles and antiparticles that flicker in and out of existence, a phenomenon often referred to as quantum fluctuations. This theory also provides the basis for understanding the fundamental forces in the universe, except for gravity. It underpins the standard model of particle physics, which catalogs the zoo of subatomic particles and their interactions. Quantum field theory, a theory that brings us one step closer to understanding the fundamental nature of the universe. It may sound like a complex dance, but it's this dance that makes up the fabric of everything we know and see. Next, we venture into the realm of Einstein's general relativity, where gravity is not a force, but a curvature of space-time caused by mass. It's quite the mind-bender, isn't it? But let's break it down. Imagine space-time as a stretched rubber sheet. Now, if we place a heavy object on it, the sheet will curve around the object, right? In a similar vein, general relativity suggests that massive objects cause space-time to curve, and this curvature, believe it or not, is what we experience as gravity. This theory revolutionized our understanding of the universe. Before Einstein, we followed Newton's law of universal gravitation, viewing gravity as an invisible force acting between two bodies. But Einstein turned this idea on its head, presenting gravity as the result of curved space-time. This isn't just theoretical musing, though. General relativity has real-world implications. It's the reason why GPS systems work, as they account for the time dilation caused by Earth's gravity. It's also why we believe in the existence of black holes, regions of space-time exhibiting such strong gravitational effects that nothing, not even light, can escape from inside them. So, when you think about it, general relativity does more than just describe gravity. It transforms our perception of the universe, challenging us to think beyond the 3 dimensions we're accustomed to, and consider the intertwined fabric of space and time. General relativity, reminding us that the universe is much more than what meets the eye. Now, let us explore the second law of thermodynamics, a law that speaks about the direction of processes and the inefficiency in energy transfers. This law is all about predictability and inevitability. It gives us insight into the natural progression of systems. It's like the ultimate spoiler alert for the universe, revealing the endgame of all physical processes. Let's take a moment to appreciate the gravity of this law. It tells us that, in an isolated system, things will always move towards a state of higher disorder or entropy. Think of it as nature's preference for chaos over order. If you've ever tried tidying up a room only for it to become messy again, you've experienced this law firsthand. But it's not just about messy rooms. The second law of thermodynamics has far-reaching implications, from the way our engines work to the lifespan of stars. It's the reason why we can't have a perfectly efficient engine, why heat always flows from hot to cold, and why, in the grand cosmic scale, stars will eventually burn out. This law also gives us a sense of direction, a flow to time. It's why we can remember the past, but not the future. It's why we grow old. It's why everything in the universe marches inexorably towards a state of greater disorder. The second law of thermodynamics, the law that governs the flow of time. Finally, we delve into Heisenberg's uncertainty principle, a principle that defines the limits of precision in the quantum world. This intriguing concept was introduced by Werner Heisenberg, a key figure in the development of quantum mechanics. Heisenberg's uncertainty principle tells us that we cannot measure with absolute certainty two complementary properties of a quantum particle at the same time. These properties could be, for instance, the particle's position and momentum, or its energy and the time of measurement. The more precisely we try to measure one of these properties, the less precisely we can know the other. It's as if the universe itself imposes a fundamental limit to our knowledge. This principle is not due to any technological limitations or measurement errors. Rather, it's an inherent feature of the quantum world, a world that behaves in ways that defy our everyday intuition. It's important to note that this principle doesn't apply to macroscopic objects in our daily lives, but to tiny particles at the quantum level. The implications of Heisenberg's uncertainty principle are profound. It challenges our classical deterministic view of the world, where everything can be predicted with certainty if we know the initial conditions. Instead, it ushers in a probabilistic view, where outcomes are determined by probabilities, not certainties. Heisenberg's uncertainty principle, a testament to the inherent uncertainty of the quantum world. Now, how do these laws connect and interact with each other? This question has intrigued scientists for decades, sparking the pursuit of a grand unified theory. At the heart of this quest lie general relativity and quantum field theory. These two theories, seemingly at odds due to their disparate scales of study, are both crucial in explaining the workings of our universe. General relativity elegantly describes the macrocosm, the vastness of space and time, while quantum field theory delves into the microcosm, the world of subatomic particles. Yet, scientists believe that there must be a deeper theory, a grand unifying theory, that can reconcile these two realms. The second law of thermodynamics also plays a significant role in this quest. It suggests a directionality to time, a one-way street from order to disorder, from low entropy to high. This has profound implications on quantum states, which are often seen as time reversible. The concept of entropy and the increase of disorder challenge our understanding of quantum mechanics, leading to fascinating discussions on the nature of time and reality. Heisenberg's uncertainty principle, on the other hand, introduces an inherent limit to precision and certainty. This principle is not just a feature of quantum mechanics, but a fundamental aspect of our universe. It reminds us that there are limits to what we can know, a notion that humbles us in our scientific pursuits. These theories also influence modern technologies, scientific research, and philosophical inquiries about the universe. From the development of quantum computers to the search for dark matter, from the debate on the arrow of time to the contemplation of the meaning of existence, these four laws of physics are interwoven into the fabric of our understanding. These four laws, each unique and complex, are all part of the grand tapestry of our understanding of the universe. So there we have it, an overview of four complex scientific laws that govern the universe. We've unraveled the framework provided by quantum field theory, the dance of subatomic particles that make up every bit of our universe. We've navigated the curvature of space-time, a marvelous concept brought about by Einstein's general relativity. We've faced the inevitable increase, the second law of thermodynamics, a law that predicts the direction of processes and the inefficiency in energy transfers and transformations. And we've grappled with the limits of knowing, the enigmatic Heisenberg's uncertainty principle, which sets a fundamental limit to precision. These laws are not just abstract concepts, but the very rules that dictate the workings of our universe, influencing modern technologies, scientific research, and philosophical inquiries about the cosmos. Thank you for joining this journey through the laws of the universe. If you enjoyed this video, don't forget to like and subscribe for more fascinating explorations into the world of science.